So we can just give everyone another minute to join the session. And then whenever Conrado feels he can start.
Okay, good morning, everybody. I have the pleasure to present you Valeria Nicolosi from the Trinity College in Dublin. She is one of the more reputed scientists in his area of interest, and she's going to delight us with a talk about how to play with atoms to make devices and how to characterize them. I let now the word to Scott that will present the talk. Thank you, Valeria.
Thanks, Conrado, and thank you, Valeria, for giving us the talk today. So just to say a little bit about Valeria before she starts her talk. So Professor Valeria Nicolosi is a professor of nanomaterials and advanced microscopy at Trinity College Dublin at the School of Chemistry, and she's also principal investigator at the Centre for Research on Adaptive Nanostructures and Nanodevices, CRAN, and the Centre for Advanced Materials and Bioengineering, which is known as AMBER, I believe. Her interdisciplinary research, it focuses on low-dimensional materials, including graphene. She received her degree in chemistry. She's a chemist by training, but her PhD, her doctoral degree, is in physics from Trinity College Dublin. Her degree was from the University of Catania in Italy. But shortly thereafter, she was awarded with a Marie Curie in 2008. And in 2012, she became a research professor at the School of Chemistry in Trinity and at the School of Physics in Trinity College Dublin. And at the same time, a visiting science in the Department of Materials at the University of Oxford in the UK. So Valeria Nicolosi is Ireland's only 6-time ERC awardee. She obtained her starting grant in 2011 and then a consolidator grant in 2016, and then thereafter 4 additional proof of concept grants. So that means that she's secured a total research funding of more than 20 million euros over the last 10 years, which is quite incredible. And broadly speaking, Valeria's research, well, it examines the processing and characterization of nanomaterials for the development of new energy storage devices. And her research is mostly focused on the synthesis and exfoliation and characterization of layered materials. Her areas of expertise include atomic resolution, aberration correction, electron microscopy, and liquid phase processing of low-dimensional materials. And so her group has developed functional 2D and layered materials for cutting-edge applications like high-efficiency transparent batteries, supercapacitors, conductive inks, and smart wearable electronics. And it's safe to say that Valeria is a true pioneer and an inspirational leader. And something that strikes me is that we're watching her career unfold in real time. I think we easily become accustomed to reading about research outputs from researchers and their publications and maybe in the news and magazines, and reading about their achievements and awards and biographies and in moments such as these. But Valeria's had to forge her own path to success, and it's quite unbelievable that she's actually the first chair or female chair in chemistry at Trinity College Dublin. Is that right? And we're talking about 2020, so that's quite incredible. But it's clear that she really loves chemistry and research and turning scientific ideas into reality, and the enthusiasm and creativity that she brings to research makes it seem quite effortless. when it's quite clearly not. And there's a lot of blood, sweat and tears goes into forging those paths. So it's a real pleasure to have you here today, Valeria. Thanks very much for accepting our invitation, and please, whenever you're ready, you can go ahead and present.
Thank you very much, Scott, and everyone who is involved in the organization of this seminar series. I would like to start by saying what a great pleasure is to be here today, and what a big regret is not to be there in person. I would have loved to be there and having the chance to speak with many of you. Thank you also for these wonderful words of introduction. And I'm delighted to be able now to tell you a little bit about the blood, sweat and tears of the last few years and where they got us so far. So I'm gonna share my screen now. So we tested this before, hopefully everything will work well. So I'm going to get a pointer. So hopefully you are now able to see my screen. So this is, so I'm going to tell you a little bit about our work in processing of two-dimensional nanomaterials and the applications that we have been seeking in the last few years. So before, I know that people like to finish their talks by acknowledging their group members. However, I would like to actually start with them, because these are the people who are actually in the lab doing all the work. As a professor nowadays, I'm just bulked behind my desk writing grants, papers, teaching, and meeting with them to create the ideas and discuss the work. But actually, these are the people who do all the work. This is the very last physical photo we took before the COVID really forced us not to meet physically in person anymore. So this was December 2019. And this is the last photo that we took at this year's Christmas party, of course on Zoom. But these are really the people who really need to be acknowledged, and every single one of these people been involved in the work that I'm going to present. So what we do in the Nicolosi group, we work with two-dimensional nanomaterials, low-dimensional nanomaterials in general, and we do everything from synthesis of these materials, liquid phase exfoliation. I'm going to tell you a little bit more about that in a couple of slides. We do high-end characterization because of their need of really correlating the atomic structures of these nanomaterials to their ultimate properties. And then we focus a lot on devices, making devices for energy storage, but not only. And I will show you a few things later on. So I'm going to touch upon all these leaves. So everything started really more than 10 years ago when we worked on ways of exfoliating layered materials in a feasible, easy quantity, easily obtainable quantity. So up until then, well, back in 2006, graphene had been discovered by the Scotch tape method. And this was, of course, a revolutionary discovery. A material that was thought to be an existent was made for the first time by Scotch tape. So from a fundamental physics and chemistry perspective, that was a massive change. Nevertheless, you all understand that making materials with Scotch tape was not ideal for real applications. So what we were capable of doing, and this goes back to my first postdoc work, was really applying everything we had learned for my PhD thesis. And we learned how to take, we had learned it for carbon nanotubes, but we applied it to layered graphite. And what we were capable of doing was taking commercial graphite flakes, nice and thick, and we could select a range of different organic solvents, which were very, very common, but were interacting very, very well with the material. And then by using sonochemistry, a simple sonic bath or sonic tip, we were capable of agitating really this dispersion, allow the solvent to interact with every single layer in the layered crystal, and then take it apart basically and induce the exfoliation in that way. When you do centrifugation, you end up with a very nice stable dispersion like this one that I show here in the center. And this is what we're going to talk about a lot later on in the talk, as I'm going to talk about this in terms of inks. This way of manipulating and processing the layered crystal into single and few layers sheets was really a revolution in a way that allowed us to produce these materials in quantities that are workable with. And this is what we do in my group. We really use these materials now in real world applications. And this method here doesn't take more than half an hour. So in 2014, we partnered with a company based in the UK, Thomas Swan, who wanted to take the science that we have produced in the lab, these 10 milliliters vials that we could produce, and upscale it for commercialization. So we developed these methods which went away from sonochemistry. We went away from sonic baths, which are really not very easy to upscale. And the method worked extremely well with shear mixing. And this is, in fact, the method that the company is using to commercialize graphene now. And this is a small intermediate upscaled version where they are capable of producing 3,000 liters in about half an hour nowadays. With the same concept, we have moved on in the years, and with the concept, following the concept that really graphite is not the only layered crystal in nature. There are hundreds and hundreds and hundreds of layered crystals. I remember a few years ago, I was asked to write a review article for Science about liquid phase exfoliation of layered crystals. And I counted at that stage, and that was about 10 years ago, I counted about 500 layers crystals. And with the years, we have been able to move on. And this is a very short, a snapshot of some of the materials which we have been able to exfoliate. Different colors show different properties, really. The wonderful thing about these materials is that they're really building blocks of electronics and devices. Some of them are metallic, some of them are semiconducting with all different sorts of band gaps. Some of them are insulating, some of them are brittle, some of them are mechanically robust, some of them have different optoelectronic properties. So really, these are the building blocks that allow us to add functionalities to our devices. And we pick and choose the material depending on the type of device that we want to use. So I always describe the 2D materials field as a zoo, really. You have a lot of different species, a lot of different families. And what we do is we take the 2D materials zoo, we synthesize them when they're not available in the market as a raw material. We do liquid phase exfoliation. Then we move on to devices, but before there is a very, very important link, which is crucially characterize what we get by TEM. And this is something that it's very, very fundamental, but it's extremely important for us to understand how the materials work and why they work in a certain way. So, for example, we were capable of characterizing these semiconducting 2D material, MOS2. And what we understood, for example, from this very early characterization, these are aberration-corrected STEM images of one exfoliated flake. What we realized that the flakes are actually not, they're nice to work with, but they're not exactly uniform in structure. For example, we could see that in the same sheet, you had some stacking differences. For example, in this area of the sheet here, you see this hexagonal structure here with the middle position occupied. That shows that basically these layers were shifted in a way that you have half a unit cell shift. while towards the edges here, you could really resolve these hexagonal patterns here, where the middle position here in the hexagon was not occupied, really showing this sort of A-B stacking, where each atomic column was on top of the previous one. So what that tells us, basically at the very, very start of our journey with 2D materials, was that liquid phase exfoliation is a fantastic method to produce these materials in a plentiful and fast way, but is not an exceptionally good way to create perfect materials which are electronically consistent and uniform, because all these stacking faults and different stackings would resolve in different electronic properties or really electronic barriers. So we understood earlier on that if you want to use these materials for transistors or for elegant IT devices, this would have not been a type of material that was useful. So this is the type of correlation between structure and properties that we are seeking to get. So this was a very, very crucial thing. Another thing that we learned, for example, this is an aberration corrected STEM image of a single layer of boron nitride, which is an insulating material. And we could see that here, what you see is that the contrast scales up with the atomic number of the atom that you are looking at. So the brighter dots will be heavier atoms, and the weaker dots here are smaller atoms that scatter less. So we could, for example, see in this insulating material, which is HBN, hexagonal boron nitride, that you get a very, very nice crystal where you have nitrogen, boron. You could really assess these things, but you also see that again, liquid phase exfoliation, which is the method this was obtained, was not a perfectly clean way of making it. Why? Because there were some deviations from the perfection of this structure. For example, if you look at the intensities of these atomic species here in this hexagon, you could see that these are the intensity here. It's stronger than the boron atoms, but it's lighter than the heavier nitrogen atom. So the atomic number was somewhere in between. So if you take an intensity profile and you track the intensities of all these atomic species going from here to here, you see that is boron, nitrogen, boron, nitrogen, boron, nitrogen, until you actually hit these atoms here, and their intensity is intermediate. And you can assess with 99% certainty that these are carbon atoms. So we actually had the sonication really made defects, and these defects were filled by carbon atoms that were probably coming from the solvent that we used. There were other deviations. For example, this is an atom here that is much brighter than the nitrogen that we could see here. So again, if we take an intensity profile, we could see that is a boron, nitrogen going all the way down until we hit this atomic species here. And this is the intensity that corresponds to it. And it's much heavier than nitrogen, and is actually oxygen here. So again, we created some oxygen inclusions in our lattice. So all we learned was that liquid phase exfoliation created these structures that were really not perfect. Once again, not perfect, and the electronic behavior of this material was indeed changing with these inclusions. Well, we learned that, for example, carbon was always replacing pairs of nitrogen and oxygen, never one atom only, always pairs, and that oxygen always replaced nitrogen. So we learned from this that we could indeed start tuning inclusions of carbon, and by doing that, we could shrink the band gap, really, and we could go from an insulating material to an heavily doped with carbon boron nitride, shrinking the band gap. And this was something very, very useful to know when some colleagues went ahead and did some devices with it. Another thing that we could use was aberration-corrected STEM microscopy to really track the synthesis of this material in situ in a microscope. And not sure if there is, it's supposed to be a video starting, not sure if it starts. Well, you could see here, if you would have been a video starting, we could have seen that you could see the synthesis of this material happening, and now MnO was turning into MnO2 as we went. And this was a very, very important result, because we use manganese dioxide a lot in our supercapacitors applications. And understanding the equilibria that happens when you synthesize this material and the stoichiometry balance that you get with MnO, it's extremely important. So we could start tuning the temperatures at which we could synthesize MnO2. A very, very interesting materials that we lately, more recently managed to exfoliate is black phosphorus. Black phosphorus has been getting a lot of attention because it has extremely interesting electronic properties similar to graphene. The downside of black phosphorus is that it really degrades extremely fastly and easily in presence of oxygen. So what we actually showed was that, yes, by liquid phase exfoliation, we can indeed exfoliate raw black phosphorus, and we can get few layers sheets, and their atomic structure is nice and pristine. What we learned as well was that we could select some solvents that really stabilized the material and really delayed the degradation. So rather than having a few minutes lifetime, we could extend it to months even. One thing that was unexpected, and this is also part of fundamental science, understanding the unexpected and using the unexpected, was that when you do high resolution microscopy on a material, this material needs to be extremely clean. If you have any residual solvent, that ends up into contaminations, and the contaminations simply do not allow you to resolve atomic resolution. You simply are very, very bad for achieving resolution. So what you normally do is you deposit the material on a TEM grid, and then what you do is you bake the material in a high vacuum, and you induce the evaporation of the solvent. Something that we didn't expect was that when we kept a TEM grid with the exfoliated black phosphorus at 100 degrees for a couple of days to evaporate the solvent, we realized that there was this sort of contaminations happening, these strikes here happening all over the place. And we noticed that they were always starting from the place where the exfoliated material touched the copper grid. This was something very, very, that turned us crazy. We looked for what was happening for a long, long time. And we tried to reproduce that in situ. So we sprinkled, for example, some copper nanoparticles on the TM grid, and we heated the material in situ in a TM. And here, guys, this is I'm going to replay it again if I can, a TM live, basically, and in situ. You can see these lines growing. If you follow my cursor here, my pointer, you will see a line, for example, happening in here. One is growing just now. So we could see these lines growing under our eyes, and always starting from copper. So we looked at it at the aberration corrected stem. We looked at these lines, and for our great surprise, these lines had an amazingly well-ordered structure. So you can see how ordered this structure is and how periodic it is. It was quite a discovery. And it goes straight up till the end of the layers where the edge, and then it finishes with the edge. It was impressive to see how structured it was. We understood by doing yields that indeed these lines were indeed made of copper. There was no phosphorus, well, it was phosphorus all around. So it was a phosphorus sheet with no oxygen at all, was not oxidized. And we could track this by being made of copper. So it was really the copper diffusing along the structure and creating these very ordered anisotropic structures. And it was interesting to see, here is the same structures from two asymmetry directions. Here, by simply tilting 17 degrees, you go from this asymmetry direction. The width of the wire here is, I will call them wires for now, is 0.4 nanometers. And you get to this by tilting 17 degrees, you get to this asymmetry direction, which is giving a width of 0.36 nanometers. Again, it was interesting to see how some of these heterostructures were not perfectly straight. You could see this undulated, irregular way. We understand that this is not a scanning issue because this is actually a very straight wire next to it. If there was a scanning issue, it would have been undulated all over the place. So it was extremely complicated structure to resolve. These undulations always had a sort of a 2 nanometer periodicity. It was quite intriguing. So we did a lot of simulations. We did a lot of DFT calculations to understand what was happening. And we understood that this copper always grew along the 0-1-0 direction. And it was never observed to happen in any other direction. And it really followed the template structure of the black phosphorus. It always went on these interstitial positions here. What we also understood by doing some image quantification with our colleagues in Antwerp was that we could quantify, and if we did the quantification of the images, build the structure through our CVD, through our DFT calculations, and then do the experimental imaging, the image simulation, what we could see actually was that the matching structure was not a 2D wire, a 1D wire really, but it was a 2D wall basically. We had a heterostructure growing across the thickness of the whole 2D material, if you wish. So it was interesting because the very, very first thing that one might have thought was that these were wires which were growing on the surface, for example, and just instigated by a temperature gradient. This was not the case. Indeed, actually, we were building copper walls into our black phosphorus structure. And what we understood was that by doing this, we were actually creating structures that were fully metallic. And we could do some nice engineering there. So we are now in the process of trying to build devices with this, which is a very, very interesting and complicated matter. What I want to focus on now in our second part of the talk is the applications. And I'm going to introduce you a new kid on the block, a new type of 2D material, which is, we call, it's a family of 2D materials, which we call MXenes. These are actually coming from a slightly different type of layered crystal, not as the ones which I showed you before, which are van der Waals layered crystals. There you have weak van der Waals forces between the layers. Here what you have is a 3D crystal layered, where you have covalent bonds between the layers. So what we do here, we do some HF etching of these layers, and we go from a crystal of this type, the max face, to an accordion type of expanded structure where we have etched away the middle bonds basically, and we get this sort of accordions. Once we do that, these are made of titanium carbides basically, with all different sorts of stoichiometries. Once you reach these accordions, exfoliating them, it's extremely easy. All you need to do is put the material, this is simply water, and what you need to do is a simple handshake, no sonochemistry, no shear mixing, nothing of that type. And all you get is a very nice and stable ink. extremely concentrated, and this is what we use for a lot of our applications. So these are the types of layers that we get, nice and thin, much thinner than what you actually get with van der Waals structures, and much wider as well. You get to the micron size, several micron size. Normally, liquid phase exfoliated sheets, van der Waals materials do exfoliate in much smaller fragments. So what we have been able to do is really use these inks for a lot of different types of applications in the energy storage space, but not only. I will show you a few examples. So this is a work that we opened, we really opened up a lot of possibilities for us. It was the first time that we used these inks as transparent conductive material, really to build transparent foldable conductive supercapacitors. What was nice about this work was that we really managed to coat a full PT substrate with these MXene inks, then coat it with a solid electrolyte, gel electrolyte, and then assemble a second layer of the other electrode all on it. And because these MXenes are so nicely conductive, so good at electrochemistry, and so transparent, really, we managed to build these very, very large devices. Normally, supercapacitors are tiny, like in centimeters. So it's very, very hard to actually get large devices like this to really work. And what we managed was to assemble a full device of 2 electrodes and electrolytes. This is a full electrode device. This is overimposed on my postdoc mobile phone to show you really 99% transparency. And this is really the electrochemical performance of this device that shows you how it is electrochemically active, really at even high scan rates. Even you can push it up to 500 millivolts per second, which means fast charging, discharging, and you really don't get any resistive behavior. It really works nicely. This was a groundbreaking work for us because it really opened up a lot of possibilities for us. And we did take advantage of these inks that were so easy to manipulate. For example, we wanted to really test the capabilities of these inks in a very, very fast way. So what we did was we built a lot of different stamps by 3D printing, normal fuse deposition method stamps. And what that allowed us was to build these stamps with all different geometries and different, we like a lot interdigitated geometries like these ones, because allows us to maximize the surface in contact with electrolyte and therefore increase in capacity that we can get. So, and all you can do once you get the stamps is dipping the stamp onto the ink and then really stamping away on any sort of surface. So here, for example, are real devices that we stamped on paper. And these devices do indeed work. This is the proof. Here is the device on paper. Here is the printed paths. Here is where the stamped paths, and here is where there was no ink. And indeed, here we pushed the device up to 200 millivolts per second. You start getting some resistive behavior here, but at lower scan rates, you really get a fast response and a lot of capacity. And the wonderful thing is that these devices are fully bendable. Here we bent them up to 180 degrees and the performance is not changing at all. So here what I show is the areal capacitance as a function of scan rate and the volumetric capacitance as a function of scan rate. And here we compare these devices, the blue curve, to other devices that were present in the literature that were manufactured in other ways, laser inscription and things like that. And we can get a much higher capacitance, both areal and volumetric. And what was also nice to see was this cyclability stability. We could cycle up to and more 10,000 times, and we could retain 94% of their areal capacitance. So really durable, really resistant, and really working at high specs. Well, we also used the same concept. We used exactly what the Babylonians did back in the 18th centuries before Christ, where they were manufacturing really these beautiful pieces of art. They were inscribing their roles and then using them to create their art in a fast way. This is exactly what we did in our case. We printed this by fused deposition method, these rolls, and then loaded the ink inside, and there you go. You could, within seconds, you could manufacture and rapid prototyping devices to test in a faster way, not possible really. And these devices do indeed work. Again, beautiful electrochemical behavior, very high areal capacitance, up to high scan rates. Again, we can get up to 100 millivolts per second. Yes, you get resistive behavior at that stage, but about 50 millivolts per second, you have a nice and square capacitive behavior. And from there, we moved on to, again, trying to create more and more complex devices. Once we knew that the inks were working, the inks were having a very, very good electrochemical performance, we could afford pushing performance. And indeed, we developed methods of loading these inks in our printers, and we could start engineering complex devices by either extrusion printing or inkjet printing. And these are the devices I'm going to show you. So we really loaded these inks in our printers, printed our devices, cast the electrolyte on top of them, print another layer of device on top, and then really test them as devices. This is an example of some devices that we printed. Again, we love interdigitated devices because allows us to reach higher capacitance, higher surface and higher capacitance. Here are devices printed in series and printed in parallel, so shows you the versatility of this type of very, very fast way of making devices. And we could see that, of course, the more layers we were printing, the higher the thickness was getting. Of course, the thicker was getting our device, and the more conductive was getting our device. Here is how the resistivity drops with the number of layers. Already printing 5 layers, we could reach a conductivity of about 2,700 Siemens per centimeters, which is really high. And it was really resistant to bending. We could really bend several times up to 180 degrees, and the conductivity was not really affected. And here several hundreds and thousands of bending cycles, and the conductivity was always stable. What we could see was that indeed these devices worked wonderfully as supercaps. Here is the areal capacitance of devices only with 3 layers printed, and with a gap between the fingers in our interdigitated material of 89 microns. And we could push up to 500 millivolts per second, and indeed very nicely capacitive behavior. Here is how the areal capacitance performs with current density for different deposition passes, basically. So we could go from one deposited layer device of about 3.5 millifarads per centimeter square up to 43 millifarads per centimeter square with only 5 passes, which was really well performing. We were very happy with this result. This was indeed also what we managed to print out of extrusion printing. This was very, very good because with extrusion printing, you can simply print inks based with water, not organic solvents like in this case for inkjet printing. And we could really print any sort of device with any shape, or open your imagination, you can start printing these devices with any geometrical shape or that you like. Again, printing on paper, PET, whatever substrate you like. And again, you can see how nicely the ink is printing. And if you go on to performance, again, we can decrease massively the resistance by printing more layers. We can reach very high conductivity by printing more layers. And you can print these devices in series, in parallel. The freedom of having printing devices is that you can really print the device in the configuration you like. What I show here also is that how resistant these devices are. Here we use Scotch tape to try to peel off the ink from the piece of paper after we printed, and indeed there is no residual at all. Once it's printed, it's nice and stable. Here is what we compared the areal capacitance of our devices, inkjet printed and extrusion printed, to other devices that were made in literature by other methods. And again, we could reach much higher areal capacitance. And here is the energy density as a function of power density, so a Ragone plot. These are all different references that we found in literature, the closest ones. And here is this work where we could really store way more energy, and we could achieve much faster response, so power density. This is how, again, the bendability of these devices was really an advantage. You can see how the electrochemical performance is not changing minimally with bending. Here we bend at flat, 60 degrees, 120 degrees. This is a potentiogram that we collected at 50 millivolts per second, and you can see that there is no really any effect on that. What about batteries? Well, we wanted to pursue applications in batteries, and not only supercaps. And when you think about batteries, you really think about what is the main limiting factors, why our batteries cannot perform better nowadays. And there are two things that you need to guarantee to the electrode. One is that the electrode is electrically conductive, because that's how you deliver charge, and that they are mechanically robust, because they need to withstand lithiation and dilithiation, charging and discharging. Also, you want to deposit, you want your electrodes to be as thick as possible. And because the more material you have, the higher is the energy you can store. But the problem is that with the conventional materials that are used for electrodes in the market, that you cannot go beyond a certain thickness, because you start getting this sort of what we call critical cracking behavior, where the thickness is getting so high that the electrode starts falling apart. So we thought how to solve this issue, and we thought that we could have some solutions towards these 3 points. But also, we needed a very good material for batteries, and indeed, silicon has been one of the materials that has been suggested as an anode for batteries for decades. But the community kind of dropped it in aside, because it was not lasting very long, in a way that silicon has a very high theoretical capacity. However, when you charge silicon particles, they expand their volume of about 400 times. And when you discharge it, they start cracking, because their volume goes back to this 400 times less. So, and then eventually, if you do it for many cycles, you actually get pulverization of the anodic material. So what we thought was, well, how can our 2D materials help this? And there are some solutions out there in the literature. For example, one way was to mix the silicon nanoparticles with carbon black to give conductivity to the electrode, and a polymeric binder that was giving, is supposed to give more mechanical stability to the electrode. But this is not a very good solution. So what we did was actually replacing the conductive additive and the polymeric additive with our MXenes. And we could do by simply mixing the two things together, silicon particles, MXene inks, make a slurry, and then cast it onto a copper foil, which is our current collector. And what was nice to see was that the sheets of our MXenes were really wrapping and covering these silicon particles and forming sorts of blankets around them. And this was really what allowed to give mechanical stability to these batteries, because the silicon didn't have chance to expand 400 times and then contract, because these sheets of MXene around them really constrained them volumetrically, and also provided good electronic electrical conductivity. Here is an example. We did manage to use MXenes both for the anode and for the cathode. Here is the cathode material, NMC, with the conventional polymeric binder and carbon black as a comparison. The maximum thickness that you can get is about 300 microns, and then you start getting the critical cracking that I was telling before. The electrode is falling apart. However, when you use MXenes, you can get up to 1 millimeter, and you still have an intact and pristine electrode. Here, only 1% of MXenes were added. And again, I'm not going to go too much and bother you too much with this, because, but basically what we could achieve was really strong electrodes by adding only a few percentages of MXenes. We could increase their conductivity of about 1,200 times, depending on which MXene we used. And also we improved the tensile toughness here of about 40 times. This was really the game changing that allowed us really to reach theoretical capacitance. So here is show the response of these anodes as a function of the mass loading here. And what it's nice to see is that you get very nice asymmetric galvaniostatic charge-discharge curves. Really, the theoretical limit is reached and maintained up to about 5 amps per grams. And this means that you have a very nice high rate response. If you looked at the areal capacitance that we could achieve, we could really achieve the theoretical limit, which is about 12 milliamps hour per centimeter square. So there was a state-of-the-art type of response. The cycling performance, it's something that should be improved, and we're working to improve. We could cycle them hundreds of times, but still we want to get them longer. Here is a comparison between our devices at different mass loadings and some reference materials. So again, we overcome any limit that has been reached in literature so far. And this is actually something that it's very, very important to stress. And then the specific capacitance lifetime, a low mass loading and high rate was outstanding. If you look at the areal capacitance here as a function of the mass of the active material, this line, the horizontal one, it's really where traditional commercial batteries stand. So you can reach about maximum 40 milliamps hour per centimeter square, while we could well go beyond and above that. So this is where we get that this material is really working well. So we deliver high areal capacitance to the electrode, and also because we can achieve very high mass loading of silicon, which is the anodic material, we can decrease the portion of inactive components, such as the current collector, the separator, and things. So we build full batteries, and effectively we could reach very high specific capacities at cell level, a full battery level. So up to really theoretical limit of about 800 milliamps hour per gram. So this was something that really pleased us. And we are still working on that. We have done quite a lot since, in about a year, but I won't present it because it has not been published yet. What I want to close up with is some other applications we are seeking. For example, we are using MXene inks to make hydrogels with polyacrylic acid and amorphous calcium carbonate. We link them and we form some lovely hydrogels, which are nicely porous. They are hydrophilic, which means that it's very good for certain applications. It's always good to have some water-rich environment, especially if you want to use this for MI shielding, electromagnetic interference shielding. And this is what we thought was an application for us to seek for these hydrogels. And these are some nice photos that show you how workable this and stretchable these hydrogels are. Very nicely stretchable, you can get them into assuming any shape, and they're fully printable. And we are seeking applications at printing level. And they can adhere and take the shape of any object you like, even non-regular shapes. So this is something that really has a lot of potential as MI shielding to coat and avoid electromagnetic interferences and things like that. Here is on a finger, and you can bend it, it's intact. If you fix it with adhesive tape, it's the adhesive tape that will break when you bend it. They are self-healable. Again, you can take it apart, you can put it aside, and after 1 second is healed. And this is very nice because this is conductive, so you can use this to make contacts and break contacts and then heal the contacts, and you can track that with electrical conductivity. You can light up the LED, switch off the LED, light up the LED when it's healed. We have been, you can track that, you can track how we can make it more and more and more electrically conductive, increasing the load of MXenes. And you can see how good this hydrogel is at shielding terahertz radiation, for example. Only 6.5 weight% of MXenes are already blocking almost all the terahertz radiation here. And by 8.5 weight% of MXenes, you get no radiation leaking anymore. This is, in our opinion, this is because you get this nicely porous structure, you get the terahertz radiation gets in, it starts penetrating and it starts getting scattered and reflected, and only very, very tiny little bit is transmitted away. The rest is dissipated. Because the nice conductivity, we managed to use that as a strain sensor as well. And we could see that, again, you could track the conductivity or the resistivity as a function of the tensile strain. And we use that to actually make all sorts of motion and pressure sensing. Here is on a finger. You can really see the bending on the finger when it goes on and off. Here is put on a arm that is bent in this way, and you can track the motion. Here is here in the throat, and you can track swallowing, for example, the 3 phases of swallowing. Throwing of the forehand, you can see the expression lines moving. And also as a pressure sensor, here it can sense a water droplet that is casted on top. And here we are writing with a pencil different words on it. So okay, no, and yes. And you can really see the fingerprints of the pressure sensor. So this is to show you that really there are a lot of different possibilities that we are seeking well and beyond the energy storage space. I'll show you some, to finish off, a couple of nice projects that we didn't envisage to start with industry. For example, we partnered with Sub Miller, who wanted to use our 2D materials as a gas barrier to sell their beers, not in heavy glass bottles, but in plastic bottles. Because you would actually be able to transport this beer across the globe with a much lower carbon footprint because it's much lighter. The problem is that when you put beers in plastic bottles, it's not like other fizzy drinks like Coke and things that in this case, CO2 really goes out very fast, and within a month, the gas is all out-leaked. And also, when you have out-leaking of gas, you have a change in taste in beer. So they didn't want that. So we partner with Sub Miller, which is a huge manufacturer of beers, Carlsberg, Miller, a lot of different sub-brands are under Sub Miller. And we used boron nitride sheets to embed that, and now they are working how to embed that in their production lines. We also partnered with a company in the Formula One racing loop. I cannot say the name of this company for copyrights and for IP restrictions. But basically, this company read about our nanomaterials in the newspaper, and they wanted to know whether we could have some 2D nanomaterials that could be sprayed in the rims of their wheels, because they wanted to dissipate the heat as quickly as possible. Apparently, the goal was, I've never followed Formula One before, but basically they wanted that their tire was getting at the optimal temperature as quickly as possible, because that could have changed a pole position with the third place in the rack, especially for qualification laps. So what we did was we indeed, some of our 2D nanomaterials worked, and now this technology is on the races in Formula One since 3 years now. So they spray their rims and they can get much faster into the optimal temperature. Last but not least, we developed conductive, transparent, fully transparent coating for Lego blocks. This is on a white. I decided to show the white Lego block because if you actually get horrible grayish, graphene grayish type of, if it is not perfectly conductive and transparent, you would actually change the color. And here's on the black as well. So these are Lego blocks that have been coated with a transparent conductive material. And you can see that how, oops, I'm going to play it again, hopefully, nicely, and conductive doesn't play anymore, but you could have seen the LED lighting up when you were making the contact. Now they are working on this to make it safe for children, because that really brings their Lego blocks to life. They will be able to program them and making them do a lot of fancy things that we couldn't envisage to start with. So with that, I bored you for far too long. I've spoken for far too long. I hope I've given you a good overview of the possibilities out there and nice applications that have opened up by processing 2D nanomaterials in energy storage, but not only. And also, I hope I showed you how important it is to correlate structures to properties, because that is an essential link for us to understand how to use and manipulate our materials. Once again, I would like to acknowledge everyone in the group. They are the heart of the group and the heart of this work. Every single person here has produced the work that you have seen. Collaborators, of course, science, it's far too big to do it alone. And I would be very, very unfair to say that I'm an expert in everything. These are the people I've collaborated with, Johnny Coleman and Stefano Sanvito in TCD, Clotilde Kuchnot and Felice Torrisi at Imperial College, SuperSTEM with Quentin Ramas, Yuri Gagozzi and his team at Drexel, and Staff van der Loo and Sandra van Hert at Antwerp and all their group. And last but not least, all the funding I've got plenty of. Thankfully, I need to be very, very thankful to this funding. These are the entities that have allowed us to do so much and so well in the last few years. So the last acknowledgement goes to them. And I would like to thank you all for your attention and for the invitation once again.
Thank you very much, Valeria. That was an incredibly interesting talk. It's a shame we kind of can't clap or anything. That was really great. It was such a nice vision of how you go from fundamental research to proper, interesting, applied stuff. It was last night, I opened the Royal Society Chemistry World, and there was an article about super or slippery 2D materials as like super lubricants for planetary rovers as well. I think they just discovered, you know, they're great lubricants for oxygen and humidity-free environments, which
Absolutely.
I had absolutely no idea about. But it's really interesting. And you talked about the whole Formula One.
Yeah, it's incredible how many, I always like to say it's not because I had a project funded by Lego, but it really working with 2D materials, you really have a sort of Lego world, because you pick and choose the building blocks that you like for the different types of applications. You have so many properties to choose from. And the added value of being able to process them in liquid in a fast, cheap way, it's really the advantage there.
Really incredible. Does anyone have any questions? I've opened the chat. If anyone would like to ask any questions, just please go ahead and post in the chat. Just say me or your name, and then I can open your microphone easily. Just wait. I'll just ask a brief question about kind of a curiosity going back to your inkjet formulation for the, for the MXene inks. Did that take a lot of refinement, or?
Well, let's say these inks are, especially the MXenes, are really, really extremely easy to work with, in a way that there are no additives. There are no, the only thing that you need to control is the concentration of your material. And then you've seen that we managed to tune inkjet printing, fuse deposition method ink printing. You tune the solvent. But having them being able to disperse and being processable in water has been a massive advantage. The one trick with MXenes is that they are prone, if you don't know how to handle them, they get degraded quite fast when they are in water-based solvents, or in solvents that have hydrogen and things like that, make hydrogen bonds and things like that. So we did, it took about a year for us to understand how to manipulate and store and work with MXenes. And indeed, we did a very systematic and thorough study. And once we discovered what worked, so for example, we keep the inks in the fridge. If you keep them in open air, room temperature, probably in Spain, they would last even less than in Ireland. They degrade quite quickly, but if you put them in a fridge, they last for months. So once you know how to handle them, they're really, really easy and convenient to work with.
That's obviously fed right into your hydrogel work. I'll ask some questions about that in a minute, because Alodia has raised her hand. So Alodia, please go ahead.
Hi, thanks Valeria for your presentation. I've enjoyed a lot. I find your work very impressive, and especially the part for the thick electrodes for batteries. I find that very interesting. And I wanted to ask you if you have on mind any strategy to improve the cyclability of these electrodes, although it's not bad at all.
Yeah.
And also if you have the same behavior with other cathode materials apart from NMC.
So the first question is that I think we are going to try to make the electrodes a little bit more porous. And, you know, you can do that by tuning the drying time, the drying temperatures and things like that. What we wanted for this work was to keep it as close as possible to the way real batteries, commercial batteries are manufactured. The work was done in collaboration with Nokia Bell Labs. So we wanted to keep it as close to market as possible. So that's why we chose to slurry-casting, which is the conventional method to make these electrodes. So one thing that we can do better is the porosity. Also, another thing that we are working to improve is the rate performance, because we need we are trying to understand how to reach the limit. Of course, the thicker you have the electrode, the slower it is at charging and discharging. So the rate performance, you need to get that sweet spot. Of course, it's not a thick electrode will never to be able to charge it fast. But we are optimizing that. And for that, what comes into place, and also for the cyclability, is the electrolyte formulation. I think we have to go away from standard electrolytes and get the SAI formation better understood. So this is to answer the question around the cyclability and also the rate performance that I had it. The second question was if we have tried other cathodic materials. Yes, we have. We have effectively now, we went on to testing the most standard cathodes. NMC was the easiest of them, but we have tried several others, LCO and things like that. At the moment, we are limited in the performance of the all cell. We are limited, in fact, by the cathode. It's our nightmare at the moment. If we had a better performing cathode, we would actually go far beyond this performance. In fact, we are cathode limited at the moment. Cathode is very complex and goes beyond, it's very, very complex.
Thanks, Valeria.
Thank you.
So there's a couple of participants with a raised hand. Just a second. Oh, Andres, I'll allow you to talk. Your mic should be open.
Hello, yeah. Very nice presentation, Valeria. I enjoyed it very much. I would like to ask you if about the gels that you have made with the MXenes. Mm-hmm. So yeah, I thought it's very interesting new research line, and indeed I would like to know for how long they are stable in terms of the conductivity or even like the drying. And also if you have dried them, like for example, by critical drying or similar to measure like the surface area, etc. And if you have in mind to work also with this material in the form of aerogels or so on.
Yeah, first of all, it's fantastic to hear from you, Andres. Andres used to be in my group, so I'm delighted to have a question from you, Andres, and delighted to hear that you like the talk. It's always nice to hear from you. So the hydrogel is a completely a new type of chemistry that we are seeking in the group. Indeed, it's opening up a lot of possibilities, and as I said, also we are moving on to the printing of these hydrogels. It's nice because they are really nicely and stable. Actually, didn't show the stability, but we have hydrogels that we made before the lockdown last year, and then we went back 4 months later. We didn't keep them in a especially preserved way, and their conductivity was still intact, and we were capable of doing this sort of putty type of healing, taking apart, and so it was very, very good. in that sense. We are at the moment, it's not presented because we are in the process of submitting a paper on that, where we are also using another step of processing with these hydrogels, which is freeze drying. And that allows us to get amazingly even more porous structures than this and control the porosities, as you said, because that comes into play for so many different applications. So that allows to give us an extra level of control on these hydrogels. But it's definitely a very interesting and system, and we're gonna get stuck on it for quite some time now.
Amazing. Thank you very much, Valeria.
Thanks, Andres.
Raul has a question. You can open your microphone.
Yes, Valeria, congratulations. Very nice talk. Very interesting results. So in my case, I was wondering about the black phosphorus material and the tail structure of copper that you are growing on the black phosphorus. So the question that I have two questions, particularly regarding with the stability of both materials. You mentioned that the black phosphorus is very well known, that once you are out of the microscope or out of the high vacuum is oxidized, and after that is ruined, and you cannot anything. So how you are proceeding because you mentioned that you are thinking about devices and you are already applying this kind of material. So that is the first question, black phosphorus, how you handle that. And the second one, these copper structures and they are atomic ones. Usually these kind of materials, I know in gold, and I know several ones close in copper, they are very unstable, and in the case of the copper, they are getting oxidized very, very fast. What is your point with these ones?
So thank you very much for the interesting questions. Actually, this goes spot on a few things that I forgot to say. Also, for time limit, I didn't show you things. So first of all, the stability of the black phosphorus. Thankfully, we found one solvent that allows us really to be able to exfoliate black phosphorus, and then somehow the solvent it's stabilizing. It's for normal applications, it would sort of create a sort of coating around the sheets, and liquid dispersions of black phosphorus in CHP are stable for months as opposed to hours. So this is one thing that we were very, very pleased of. The other very good news is that somehow when these lines form, you don't get any sort of oxidation anymore, either on the black phosphorus or on the copper lines. They are stabilizing one another. So this is incredible. I couldn't believe it. And we have been testing these lines now for years. And it's the structure is fully stabilized. Once you get these lines growing, you don't get any oxidation at all. For example, the eels that I showed when we discovered that was copper and everything, just to give you a timeline, these were at that time when we did this work, our neon was out of order. So what we did was we shipped the grades to Superstem and also to Antwerp, to Staff van der Loo and Sarah van Hert. And they got them sitting there for quite some time, and then they looked at them, and then I said, well, hang on, I'll do some fresh analysis once the neon is get back to normal. And the eels was just identical. So there was no oxidation whatsoever, which is bizarre, is intriguing. These lines are fantastic. If only we could make junctions with them. The problem is that they grow parallel. So there are some pros and cons.
Thank you. Thank you very much.
Thank you.
Just checking that there's no other hands raised. Oh, yeah, wait. Sorry, Luis has a question. On you go, Luis.
Yeah. Okay, thank you, Valeria, for this fantastic talk. Well, it's really amazing the versatility and the processability of this kind of materials. Well, my question is just a curiosity about this, the application on plastic for improving the barrier properties of plastic bottles, for instance. In this case, how do you process this kind of layer materials in the plastic? Is a coating or is a nanocomposite? Or
it's a composite. It's a composite. Okay. Absolutely. And then again, this was another work that was done with and for industry. So we had to keep all their manufacturing procedures. So extrusion was at the end what they wanted, okay. And it was a composite that was made. And that was with boronitride because, again, it's a very good layered barrier material, biocompatible, non-toxic. So that's why we decided to go with BN.
Oh, okay, fantastic. Thank you.
You're welcome.
Thanks, Luis. Valeria, can I just ask a quick question then? I remember, for example, with this few layer, the vertically aligned molybdenum disulfide materials. Have you ever thought about looking at them for like solar assisted antimicrobial applications or anything like that? Because especially like, or any of your materials that, you can deposit them so well and incorporate them as composites and so forth.
We never thought about this type of applications. I think it would be amazing to try. Again, this is something we would have to find partners for doing it. Again, we don't have expertise on everything, but this would be another type of application that would be definitely interesting to try, certainly.
And do you think you see yourself moving into something like stimuli responsive soft robotics or biosensors with all this hydrogel work? Because I didn't know that I hadn't seen that paper, but that work's really impressive.
Yeah, I mean, the group is so large that it really allows us to go out of the box sometimes, depending on also using the expertise of the postdoc working on that project and thing. So that was really started as a sideline of a main battery project, actually. And we really identified this as a great opportunity to move on other fields. Again, sensing, motion sensing, and pressure sensing, they're very, very easy to test. So I wouldn't say that we have all the expertise to move on beyond that, but certainly these were under our remates of something we could do and measure ourselves quite easily, because really depending on conductivity, it's really, you get the response. So certainly we move out of the box sometimes.
Very cool. Really interesting. I'll just double check that if there's no other questions, I'll just pass over to Conrado then to finish up the session. Just thanks again, Valeria, for your talk. It was really nice, really inspirational, and thank you very much.
Thank you, Valeria. Just a question. You said sometimes you are moving out of the box. Did you try anything with superconducting materials?
No, we never tried any of that, actually. It would be interesting to see. Again, everything that has got to do with perfect structures, and it goes well, I think, beyond what liquid phase exfoliation can do. But certainly would be another extremely attractive field to start exploring with the right collaborations, because we wouldn't have expertise in that.
Thank you very much. Very nice talk, and we hope to have you here. I'm sure we have a lot of things to share with you and to collaborate. Thank you, Valeria. Thank you very much, Corrado. Thank you all, Scott, Raul, Alodia,
Luis. Thank you very, very much for the invitation. I really enjoyed this. And this is the real one trip I really wish I could have done in person. So certainly I would love to visit when possible. Thank you again.
Anytime, you're always welcome.